Welcome to Java Jumpstart for Scripters. This is a re-recording of a talk that I made at Skills Matter for Civic Reactor on the 28th of June 2017. To get the most out of this session, you should have Java, the JDK, installed on your computer and set up so that you can compile and run Java applications. The original aim of this talk was to provide a small taste of Java programming and also to highlight Civic Reactor's mission. These slides are a slightly truncated version of the original talk, so they do cut out Civic Reactor's mission. But by all means, if you pop back to the previous slide, there is a link to Civic Reactor's user group that meets at Skills Matter every Wednesday. Now this is quite a short and fast-paced course, so or talk rather. What it intends to do is give a very quick overview of Java. Specifically, it's going to cover a wide range of skill levels. So it's going to start off very simple, and then it's going to ramp up a couple of times quite abruptly. Hopefully so that anyone watching it would get at least something out of the video. To that end, this talk is not able to take someone from nothing to being proficient in Java, but what it does intend to do is remove a few of the roadblocks that you may get ahead of you that would cause problems in terms of sort of getting started with this. So there's three main sections. There's the fast-paced overview and where Java makes sense, sort of why you might want to use Java. There is some balance there as well as to why you may not want to use Java. Then we move into an overview of Java's data types and also a jumpstart in writing, naming, compiling and running Java applications. There is some theory with OOP and Java's architecture which is sprinkled throughout, and you'll see another highlight on the slides for those times. So what does Java give us? So Java is an enterprise language which is designed for portability. It's got this idea that you write once and then you can run it anywhere. Now, that doesn't always quite work that way. You will get some occasions where you do need to put some extra code in for platform-specific adjustments. A key thing that I've had to do is handle the case where high DPI scaling works on Mac and Windows, but doesn't quite work on Linux without a little bit of help. But generally speaking, far more portability than a lot of other languages, and the mantra does hold, generally speaking, so it is very good for portability. Now, I'm quite opinionated in terms of my languages, and I know that I may disagree with your particular viewpoint here, but I'm very, very happy about strongly typed languages. I definitely see the draw of more weakly typed languages, but I do like the extra checking that you get at compile time, with the idea that if you catch bugs earlier, it's less costly to put it right. Java also gives good concurrency support for multi-threading. Now, I put that on there specifically because if you're coming from a scripting background, then quite often you may not have looked at concurrency issues at all. So that's a big topic to get your head around. Now, while I don't have any time in this session to talk about concurrency, you could quite easily run over a number of sessions with that. It is a good place to go and have a look, at least get an idea or a feel for concurrency. Not because that's then going to make you great at actually writing concurrent programs, because the easy part with the concurrency is understanding it all. The difficult part is actually writing the stuff that works. And it's insidious, because you get all sorts of problems that only occur in a very rare set of circumstances. Java also gives you it's a classic OOP language, and with Java version 8 you now have functional paradigms in there as well. JavaScript and other languages are also bringing this sort of hybrid nature in, and it's very good for solving some of the sort of current real-world problems in terms of dealing with big data sets. Automatic garbage collection. So if you're coming from a history in C, or if you're aware of the languages such as C, C++, in those you have to manage the object lifecycle yourself. So what that means is if you spawn off a bunch of objects, when you're done with them, you manually got to go back and destroy them and clean them up and release that memory so it's available for use again. Now Java And when Java was being created 20 odd years ago, the designers of the language decided that this was a source of a lot of bugs, and as a result, they created the garbage collector. So this basically runs when it feels like it, and it collects up all the orphaned objects and returns them to the memory, to the pool. And this sort of eliminates problems with memory leaks. You may have seen that in things like games you've been playing. Over time, the application gets slower and slower and slower, and then it just falls over at some point. And quite often that's probably due to a memory leak. Java is also a big community language, so if you're looking at something like .NET, maybe C#, something like that, a lot of the tooling and a lot of the libraries are provided by Microsoft, and they're very good. It's just the ideology is slightly different with Java, and an awful lot of the time you'll be going off and getting a library from the community. And if you're coming from a scripting background, and you're used to sort of NPM and so on, you're going to be used to that sort of thing. Java also gives good stabilized support programmers in building scalable applications. It is opinionated, kind of like Angular is opinionated. So there's certain structure that's provided for you out of the box. There's certain rules you have to follow, which keeps things nice and consistent on the whole. So this is the JVM, and this is how Java provides its cross-platform write once and run anywhere concept. So what you have is you've got the JVM, which is a virtual machine that sits on top of the host operating system, whether that be Windows, Mac OS, Linux, or whatever it might be. What you do is you pick your language, in this case talking about Java, but there's a number of languages that run on the JVM, Scala, Clojure, Groovy, etc. So you perform a compilation step on your source code, and that turns it into bytecode, which is very similar to sort of the intermediary language concept on the and the CLR versus the JVM from the .NET world. And then what happens is that the JVM uses a just-in-time compiler, or jitter, to convert the bytecode into the machine language for the host that's running on. This is good in a number of ways. Most notably, you can tune the JVM, and in fact the JVM can perform code analysis, and it can alter the way it's compiling the source code, or the bytecode in this case, in order to optimize for performance or whatever else. So where does it make sense? Well, in fact, Java's used pretty much everywhere. It's a really, really widespread language. You could be used on back-end servers, so if you could have something like an Angular front end or a React front end, and you'd be calling via a RESTful API provided by Java applications. It's used on mainframes, cross-platform GUI apps, so used to be using AWT Swing, now it's JavaFX is the preferred library for that. Embedded devices, and Android mobile. Now, I put Kotlin with a question mark after this because you may be aware that Kotlin has very recently been made into a first-class language on Android. Kotlin is a language by JetBrains, who are the people that make the IntelliJ IDE. And it's designed to be a better Java, sort of improving on sort of historical kludge that comes with Java's sort of enterprisey nature. So criticisms of Java, because it's backwards compatible, which is great if you've ever written any code where you've had the underlying frameworks, etc., have had breaking changes and you've had a whole bunch of work to do to fix them. But the idea or the ideology behind Java has always been that you can take your code base and it will run on version 1, it will run on version 2, version 3, etc. But part of the problem with this backwards compatibility is that it can result in perhaps poorer feature implementation than you would get if you were able to clean slate, as some other languages such as Scala, .NET kind of tend to do. Generics, for example, of this. So generics, for instance, are implemented in a way such that at compile time, what they do is they basically throw away all of the generic information. It's called type erasure. Which may not have been the way it would have been implemented otherwise. Functional interfaces, and so on and so forth. The garbage collector, while it's great, runs when it wants to run. You can't really control that, and that results in some problems if it runs at an inopportune moment, such as while you're performing some very intense operations. It has two types, so you've got simple types and complex types, and they're treated differently, which creates an additional thought process, I suppose, that's not existent in some other languages. The built-in Java collections, after you've been using them for a while, you sort of hit upon their limitations, perhaps the design, the way, again, that some of these things have maybe grown. You do have community offerings, so Guava, I believe, is provided by Google, which is a set of replacement drop-in libraries for the inbuilt collections. There are a whole bunch, of course, more problems with Java as there are with any language. But the biggest one that people tend to whinge about is its verbosity. So here is a POJO. So it's a plain old Java object. This one contains 3 fields and a constructor, and then it has a whole bunch of getters and setters for providing the API for this particular class. So this is quite typical. The getters and the setters basically provide a decoupling between the internal operation, or the internal representation, and the public API, which allows you to vary the internal representation without touching the public API and without breaking code that is reliant upon that. For comparison, that's the same thing in Scala. It's not really, but it's kind of more impressive to show this sort of difference. You do actually get quite a lot more with that Scala code than you do with the code on the right in Java. But having said that, you don't get the same getters and setters. It's more like public fields in a way. So that's probably closer to the representation, but they're not identical. So why Java? Well, Java's been around for about 20 years. It's an enterprise language, and there's a lot of code bases that use it, which means there's a lot of work out there for a developer. If you look at these sort of numbers, matching permanent jobs, you can see that jobs advertising SQL hits the #1 spot. Then you've got JavaScript, then C#, which is sort of Microsoft's version of Java, and then you've got Java itself. The nice thing to see is that you get a nice jump from the average salary by about £10,000 when you hit Java. And the next one, which is the same sort of salary as Python, but you're looking at about half the number of jobs there. The other thing to think about with Python is that you've got an awful lot of data science jobs that will be utilizing Python. So Java's a pretty good bet in terms of a language that's been around for a long time, that's likely to be around for a long time. It's solid, it's stable, it's established, and there's fairly good salaries. So we have a quiz here. By all means, if you can answer these questions, pause the video if you need to, and then we'll open them up. So, object lifecycle is managed by the garbage collector. We've spoken about it freeing up the memory from orphaned objects, which are objects which no longer have any references or pointers to them. The 2 categories of types are simple and complex, and which we're going to talk about in a little bit. And the Java source code is compiled into bytecode, which is then JIT compiled into platform-specific code at runtime. So this is the first task for you to go and do. I recommend you go and do it if you haven't done this sort of thing already, simply because we are trying to get rid of the little blockers. So I've got tips on the right hand side. The key thing is create with your favorite text editor. You don't need to be using an IDE. Save it. There's a few key things. First one is that the name of the file must match the name of the class. So here we have a class called hello, and we must therefore have a file called hello.java that holds it. You compile it using Java-C, so if everything's set up fine, that should produce a hello.class file. And then to run that, you do Java space hello without the .class, because you're referencing the fully qualified name of the class. Okay, so data types. Java has 2 sets of data types, as we've mentioned. We've got simple types and complex types. Simple types hold the value of the type in the direct memory space that's allocated for the value, whereas complex types usually exceed this available space. So instead, what you do is you store the actual object elsewhere on the heap, and you use the direct value space to hold a reference to the memory location where it is stored. Now, I do appreciate that sometimes at that point people tend to glaze over, so I think this is best explained through a diagram. This diagram, here you can see we've got a combination of types. On the left we've got the stack. If you're not familiar with the stack, a stack type of data structure is what's called a LIFO data structure. It's last in, first out. You've basically, think of them as a stack of pizza boxes on the floor. If you want to retrieve a pizza box, you can't pull the one out from the middle or the bottom because the stack will fall over. So you can only access the element that's at the top of the stack, which is the last one that you put on the stack. So you generally have three operations with a stack. Peek, which just has a look at what's on it. Pop, which takes the element off the stack, and push, which pushes a new one on. So you push new elements on and then you pop them off. And that's what the stack is. So this is an abstraction for sort of how memory can be divided up. You've got the stack there, and then you've got the heap, which is another larger space, which doesn't operate in this stacking mechanism. So here we've got three elements on the stack, or three data types, I suppose, on the stack. You've got we've got Oyster card, travel card, etc. These are the data types for those variables. You've then got a reference for them, so I've got card 2, T card, card 1, and then the section underneath is a representation of the directly allocated memory space for that variable. So here we've got ref, and ref, which means that these are all complex types. And you can see that they point over to memory locations on the heap where the actual complex type exists. But you can actually store complex and simple types inside, or you can nest these as many times as you want inside of a complex type. So we've got an Oyster card that's got auto top up, registered amount, and travel card attached. Three of those are simple types, where the actual value is stored in the directly addressed space. We've got false, true, 6.3. You've got another complex type which points you out to yet another memory location, and then you've got string. Now, an important thing to note here is that the simple types, the ones that actually have a value directly attached to them, all begin with a lowercase letter, or they're in lowercase. So we've got Boolean there, a double, and I think there's an int on the right hand side. Whereas all the complex types begin with a capital. So you've got Oyster card, travel card, string. These are complex types. In fact, anytime you create a new class in Java, you are creating a new type. So that's why you should remember, prefix your types with capitals, or in fact, Pascal case, because if you have multiple words, you want to capitalize the first letter of each. So here's an example of some of the data types. On the left, we have simple types, and on the right, I've provided an additional one, string, and also what we call the boxed versions of the simple type. So a capital B Boolean is a complex type that simply holds a simple type. And this is how you can take a simple type and basically turn it into a complex type. Now, the reason that I've run through this is mainly there's a few behaviors that are different depending on them. So the first one is equivalence. You're probably all used to using something like A equals B. And in Java, the equals comparison operator makes a comparison on the value itself. So remember that directly attached memory space. So when you compare the two of them, it checks the values. And the values on the simple types, if they're the same, it says true. And if they're not the same, it returns false. Complex types, however, aren't holding the value there. Instead, they're holding a reference or a pointer to a memory location. And so the only time that equivalence will return true for complex types is if your complex types both point to exactly the same memory location or the same object, even if those objects do or don't hold the same actual values within themselves. So the way that we perform equivalence on complex types is through an equals method on the type. So this is something that you inherit from the base object, but you override this to set up the behavior, or basically define the logic for how an object will check against another object to see if they are the same. And the way that you call this is the first object, then the dot notation, dot equals to call the method on the first object, and pass in object 2 as an argument. Object 1 will then execute the logic to perform the equivalency check and will return true or false based on the logic that you defined for that particular type. As you can see, different behavior. Okay, so method calls we've talked about. In fact, methods and fields you access on an object simply using the dot notation, which you should be familiar from most of the other sort of languages, certainly JavaScript, TypeScript, etc. So object.doThing passes some arguments that calls the doThing method on the object and then gives it the data. It's important to note that these things are passed by value. So if you take a simple type and you pass that argument in, the value of the type is copied into another variable inside the object which holds that, which means that simple types have no side effect on the original, but this behaves a little differently again for complex types, because when you pass the value in fact is a reference or a pointer to an object. So when you manipulate that object, you are actually manipulating the object stored on the heap, and so it does have an effect outside of the scope of the method. Okay, another little quick quiz. You're happy to pause the video if you want to have a crack at these. If not, we'll just go through them. So we've done this one a number of times. We've got simple and complex types. How are each of the types named? Well, this is the camel case versus sort of the lower case. I'm going to mention, so I've got camel case and Pascal case. Camel case is lower on the first letter, uppercase on all the following words. Pascal case is uppercase on all of the first character of each word in the name, including the very first one. And in this case, obviously, the simple types only have a single word, so it's all in lowercase. How many Java data types can you remember? Well, hopefully you've had a little write down there, but here are the ones that we've covered, and uppercase the first character on each of those to get the box types. Okay, so now we've got another opportunity for you to have a crack at creating an application. So here you're to create an app.java file which contains a class. Don't forget to name the class the same as the file, so it should be a class called app. It needs an entry point to the program, and that follows the signature, public static void main, and then parameter of string array of arguments, or args. It doesn't actually matter what you call args, but convention dictates that we call it that. What I want you to do inside this is basically declare and initialize a number of variables, simple and complex. So you've got things like in age, boolean is happy equals true, integer legs equals new integer. Then what I want you to do is I want you to carry out some equivalency checks on them. So use the equals on the simple types. Try it for simple and simple, simple and complex, complex and complex, and also try the dot equals. If you pull the GitHub repository, you have a template there that you can fill in. There's also an exemplar solution in the solutions folder, just to sort of walk you through some of the stuff. So have a play with that, and then so pause the video to go and do that, and then unpause and continue. Alright, so now we're coming to a point where we're ramping up again. I've been mentioning and talking about things like classes. Unfortunately, it's always the case that no matter what order you'd sort of cover some of this material in, you're always thinking, if I'd only known this other part earlier, it would have made more sense. But in actual fact, what tends to happen is that it doesn't really matter which order you put things in. Whenever you cover certain topics, there's other things you don't know. So a class is basically, or can be thought of as a template. It's a blueprint for creating something. Think of it like cars. You've got a blueprint for a car. That is not a car. It's just sort of the instructions on how to build a car. When you actually produce a car, that is the same as instantiating or creating an instance of the object. And you can create more than one car from the blueprint for a car, in exactly the same way that you can instantiate multiple objects from a single class template. This is good because it basically follows dry, or do not repeat yourself, don't repeat yourself, which is good for code reuse. Reusing code means that it doesn't occur multiple times in your code base, and fixing bugs is easier because you don't have to fix it multiple times. Classes also exhibit encapsulation. So, I mean, basically, object-oriented analysis and design arose from procedural code in order to tackle the problems, sort of the graphical user interfaces and event-driven programming. So things like, the user clicks his mouse button. Well, now you need to handle that event occurring, and OOAD is very, very good at doing this. So what classes do is we encapsulate related information or data and functionality, or in this case methods. So because this data and functionality is related, quite a lot of it doesn't need to be seen, handled or dealt with outside of that object. So what you do is you perform something called information hiding, where your encapsulation only exposes publicly the API that you need to interact with that particular object. And the result of this is that it creates a simplification, reduces complexity of your application, and hopefully reduces the number of bugs in the code. Just as a reminder again, we're using the dot notation, the dot do, to give the dot method, and also to get dot fields that are made public by a particular class. Alright, so in Java there are a number of rules for writing classes, and you've already encountered some of them. The first is that the name of the class must match the name of the Java file. You're happy, hopefully at this point, that a method is a function residing within a class. These should be written in camel case, and I've written camel case in camel case to make that point. The Java application must have an entry point, which you've already discovered twice. That's a public static method called main, which accepts an array of strings, which are command line arguments basically. The name of the class should be written in Pascal case, which we also know from work on the data types. So packages, you can think of like an Angular 4 module, and what it does is it allows you to collate and group a set of related classes. In the same way that a class encapsulates related information and functionality, a package groups and collates related classes. If you don't define a package, the class that package is in, or the class is placed into the default package, which generally speaking is not a good thing because it makes it more difficult to unit test because you can't import it. And so generally speaking, like, try to avoid default packages when you start using an IDE. That will handle this sort of thing for you, but it's a good habit to get into. So, for you to do this, the simplest thing is simply copy the hello.java file to a new file called hello package. Change the class name to match again, remembering that first rule. Add at the top of the file the line something like package space com.civicreactor. Now, generally speaking, because packages, apart from anything else, allow us to differentiate our classes from other classes. You can think of them as namespaces as well. So if I have a class called app, if I wanted to create another class called app, I can't do it. I get a collision. It doesn't know how to differentiate them. If you put these into two different packages, there's no problem at all. So when we create our Java applications, we'll package them up. Generally speaking, instead of the default, we're using something like an identifier that identifies the organization. And this is usually something like the organization URL reversed. So civicreactor.com, for instance, would be the package com.civicreactor. So place a line like that at the top, semicolon at the end. And then you need to place the actual file in a directory structure because Java expects to find this class in a directory structure that matches the package. So you can see on the right hand side I've given the package, the com directory has a civicreactor directory, and then the hello package.java will be in that folder. You can compile the file using Java-C as you did in the same folder, but to actually execute it you're going to have to come up to the root, so you need to be above the com folder. and then you execute java space com.civicreactor.hello package, and that's going to execute exactly the same way that we dropped the .class previously when we just had the name. Although we didn't have to put a package name to prefix it because it was in the default package and that value was empty. Here we need to give it its fully qualified name, which includes the package name followed by the actual class name. So go and have a play with that, get that working. Sources there in O3 packages, and then come back. Okay, so inheritance is an important concept in OOP. The three pillars of OOP are inheritance, encapsulation, and polymorphism. And then the fourth tenet is message passing, which is how you interact with objects. So if you want to call a method on an object, you are passing a message to say, execute this code. If you're giving it arguments, then you're also passing those arguments in with that calling message. And that's what message passing is, basically. And it's how the different components of your object-oriented system communicate and interrelate. So this is the action side of things. So inheritance allows for a form of polymorphism, or subtyping, basically, where the same operations can be performed on different types. Now what this means is that you may have heard the phrase program to an interface. And what this is that if you have a subtype of another class, you can generally swap one for the other. And if you're calling an object as if it is an object that's higher in its inheritance hierarchy, then that defines the API with which you can communicate with it. Now, the actual API itself defines what methods you can use to access an object. It does not specify the behavior, which allows you to substitute different objects and behave differently for the object type that you're thinking you're dealing with. And this allows you to easily swap out the behavior. So it is important to consider the L in solid principles. So the L stands for Liskov substitution principle. And this also, the point I'm going to make is quite related to interface segregation as well. But basically, we're going to come to interfaces in a second. But however you have your parent type, if you're viewing an object as if it is that parent type, then that provides the API by which you're going to interact with the object. And it shouldn't be the case that you go to interact with an object and then you get an unforeseen circumstance. So Liskov substitution principle states that you should be able to substitute any subtype for its parent without losing the functionality in it. So one thing that would be very bad in this case would be if you implemented a method that you're required to because of the API and then either did nothing with it or threw an exception, such as a not implemented exception. So it's that substitutability which you're going to take advantage of in terms of sort of subtyping. And this lets you build sort of scalable, maintainable applications, because what you can do is you can quite easily swap out the actual concrete implementation that you're dealing with, which will change the behavior of the object without changing the API that you're doing the message or passing or the calls to. So you're still interacting with the object in the same way, but you're altering its behavior. Now you may have heard of the mantra, favor composition over inheritance. And this is because, even though I've just talked about inheritance, it can be very, very easily abused to create enormous sprawling trees. It does result in much more tightly coupled and less flexible means of providing this extension to behavior than composition does. When we come on to the next slide, we'll find a little bit more about interfaces. So, inheritance here, we've got an example. So we've got a creature, and then we've got two subtypes, a bird and a cat. The creature provides reproduce, get name, and set name, which means that in bird and in cat we get these methods for free. In fact, if they were implemented in a way that's returning the name, if they were actually implemented methods rather than say if this was an interface where they wouldn't necessarily be implemented, or an abstract class if they weren't implemented. But if they are concrete implementations, then you get them and you don't need to redefine them. However, the good rules to live by section is what I want to draw your attention to. Okay, so we've spoken about pitfalls in inheritance. So if you try and follow these rules, you should be fairly good. So the hierarchy should be as shallow as possible. Are we talking 2 levels, 3 levels, etc.? Well, it's gonna depend very much on the situation. What you do want to do is you always want to keep pushing common functionality up the tree so that it's shared, because that's going to improve your code reuse. But what you don't want to do is you don't want to make mistakes. Now, there's a deliberate mistake in this tree, for instance. The bird here. You might think, oh, right now I'm going to have a penguin, and my penguin, obviously, he's going to inherit from bird, get all that goodness. The issue here is that penguins can't fly. So if you were to do this, you've then got to do something like throw an exception on fly, or do nothing when fly, which kind of breaks the whole idea. That's definitely a code smell. You've done something wrong with that hierarchy. Okay, so be careful. The other rule to live by is that basically siblings in different tree paths shouldn't share characteristics. If they do, you probably made a mistake with your hierarchy. Okay, so if you follow those levels and always think, unless I've got a good reason for doing so, don't do it. Interfaces and abstract classes. So quite often I read on the internet that these are fairly common questions that come up in interviews. But you should know what these things are anyway, because it's going to make you a better programmer. So the interface is literally just a contract for the API through which you're going to interact with objects. It defines methods that you can message pass to. Abstract classes provide either full or partial implementation of behavior, but the key thing is that both interfaces and abstract classes cannot be instantiated. You have to declare what's called a concrete class that inherits from those, that you can then instantiate. And you're probably going to set this up in a way that where you've got an interface at the top. That's declaring the API. You're going to program to that interface so that you can swap out the classes below as needed. And they're going to maybe you've got an abstract class below that, which has shared or common behavior pushed up into it to reduce or to improve code reuse. And then you've got other types below that. Okay, keywords. Okay, so we've got 2 main keywords. You've got implements and extends. Okay, now implements is the keyword you use when you're implementing an interface. So you can see here we've got public class cat implements creature, and then on the next slide we have the abstract class or abstract creature, which we extend. So cat extends. You can only extend a single class, but you can implement more than one interface. So if you recall, I mentioned interface segregation. We don't want to have these things where down the tree something has a method that it doesn't need, want, or like. So what you should do is, rather than having big monolithic interfaces, you should break them up into smaller ones. So you might have, flying creature as one. You might have speaking creature as another one. Observable creature, these sort of things. So you split the things up, and then you can combine them up as needed, so that your object can be looked at as if it is that interface type where needed. Okay, so now there's the big or bigger go for you. There is a whole bunch of scaffolded code for you in the repo, and there's also a bunch of code with sort of exemplar solution to this stuff. In fact, if I just pop back to this slide, there's one more thing I want to point out for you, and that is the override annotation, so the @override. Now what's happening here is obviously reproduce with this method signature, and the method signature is basically the name of the method and then the parameters and their types, and that's how you differentiate these, because you can produce, or you can perform method overloading, where you change the signature but you keep the name the same. But what this override does is obviously reproduce is declared in abstract creature, or maybe even higher up the chain than that. And if we want to override it, it's very easy to make a mistake. I could have slipped my finger and accidentally typed out reproduced, for instance. And if I've got a reproduced, that's no longer matches the signature of the override. So when I try and access the reproduce method, I don't get this functionality. Instead, I get the functionality inherited from the parent class. So by putting this override annotation on, it gives you a compiler check to let you know Well, hang on, you're not overriding anything here. There's something gone wrong, and obviously in that case it would be true, and I'd fix that up. So just be aware of that. It's very useful. Okay, so your inheritance turn. Go and have a play with this. I've given you here on the slide the interface and the class and so on, but if you go and pull the scaffolded code, there's a lot more Java doc in there. Explains everything a bit better, and it provides you with the structure with which to get started. So pause the video, go and have a play, see if you can build this up. If not, go and have a look at the example code until you sort of have an understanding of that. Okay, on the previous slides, which you can also get from the repo, there is an example of how you actually create object instances, so using the new keyword to new up an object instance or an instantiate an object, so you can see how these things are used, and of course remembering the dot notation. Okay, so where do I go from here? So the first port of call really is probably going to be the Java 8 docs. Now obviously that number changes each time a new release comes out. Java 9 is imminently due. You've got resources on places like Code Academy and Udemy, Pluralsight, lynda.com. By all means, if you're in London and you wish to pop along to the community, you've got the London Java community, which are huge. And then you've also got Civic Reactor, which is our group, which is much smaller and more focused on sort of actually regularly programming and developing skills in order to produce materials for civic good. So I wish you well on your Java journey. I hope that it's been useful in some way, and that perhaps we've eliminated a few of the roadblocks in terms of getting you started. So good luck and happy programming.